Good afternoon, class. Today what we'll be talking about is section 4 of chapter 5, in which we talk about medians and altitudes of a triangle. We also get the last two centers of a triangle that we haven't talked about yet. Yes, there are 4 centers to a triangle, whereas there's only 3 sides and 3 angles and pretty much everything else, but there's actually 4 different centers. Alright, the first thing that we need to know is what is a median? If we think of what median sounds like, it sounds like middle to me, or medium, something in the middle. And that's exactly what this does. It's a segment that goes from the vertex to the midpoint on the opposite side. So a median is a segment that connects the vertex to the midpoint on the opposite side. That's all it does. That being said, the only thing that I can usually tell you about median is that this segment here and this segment here has to be congruent because it's connected to the midpoint. The first type of thing I might ask you is, can you look at a picture and tell me if a segment is a median? Well, all you have to do is make sure is that it, first of all, goes through a vertex. And that vertex, or that segment, is also connected to the other side and goes to the midpoint. So is C a midpoint? In this case, yes. This is segment AC is a median. If I go to the right over here, I'm going from A to C. It goes through a vertex, goes to the midpoint. Yep, it is a median. Here it goes to A, so it goes through A, goes to C. It does go through a vertex, but I don't know if this is a midpoint. I could try and think on this for a while, but I don't think there's any way to prove that this point C here is a midpoint. And if I can't do that, this is not enough information. So yes, not enough information. And the last one, again, it goes through A, goes to the midpoint on the opposite side. Definitely a median. For the most part, if I'm asking you just a separate problem with just a median, usually I'm asking you to look at a triangle and tell me if the shape is actually a median. That's really about the only type of example you'll see here. However, when we talk about the centroid, the point of concurrency of the medians of a triangle, there's something that happens that will take a little bit more work to get down. The concurrency of the medians of a triangle. The medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoints on the opposite side. What that is saying is, when I draw a median from B to F, a median from A to E, and a median from C to D, they all intersect here at G, called the centroid. And this length from B to G is 2/3 of the total length, B to F, always. So if you know the total length from B to F, you also know the length from B to G. Consequently, you also know the length from G to F. This is, in equation form, what this says in words. The length from the vertex to the centroid equals 2/3 the full length from the vertex to the midpoint. The vertex to the centroid equals 2/3 the length from the vertex to the midpoint. The vertex to the centroid equals 2/3 from the vertex to the midpoint on the opposite side. Something not set up here is that, hey, if length of segment BG is 2/3 of the length, doesn't that mean length of GF has to be 1/3 of the total length? Well, yeah, it does. That ends up being true. However, we don't include it in this theorem. But I know that this also has to be true. From the midpoint to the centroid is 1/3 from the midpoint to the vertex. It's 1/3 of the length. That's also true with the other two parts, EG and DG. They're 1/3 of the total length. Now, if I compare these two here, if BG is 2/3 BF, and length of segment BG is equal to 2/3 the length of segment BF, and I have length of segment FG equal to 1/3 the length of segment BF, well, this is 2/3 of a number, this is 1/3 of a number, so that means length of segment BG has to be twice as big as length of segment FG. And that's what I can say here. All three of these things end up being true. Alright, at this point, I have a centroid behind me that we'll take a look at. There's not really a whole lot to show here. But the centroid is another one that stays on the inside at all times. The only thing that these numbers over here are telling me is that this is in fact a midpoint and it is going through the vertex. They always do intersect here at point B in this case, and that is my centroid. And it will always stay on the inside of the triangle. So the centroid and the incenter are always on the inside of a triangle, no matter where you look. This length right here is a third the total length. This length right here from F to B is 2/3 the total length from F to G. And if I look at from G to B and I compare it to B to F, this length here is twice as long as that length there. That's all the concurrency of the medians of a triangle state. This is unfortunately not as neat as the other two in my opinion. But you can still move it around and just look at the pattern it gets. I believe this reminds me of Cat's Cradle. But yeah, there's a centroid investigation. And over here are the numbers just to show you that what I said is true. The length from A to B is 2/3 of the length from A to C. B to C is 1/3. So again, these numbers just verify that what I have said is true. The bigger segment is 2/3. This is 1/3 of the full length. Alright, in example 2, they tell me that G is a centroid of triangle ABC. And then they tell me 4 of the lengths. Find the length of the given segments. So let's write this on the backboard here. I have designed this so it should come out to all whole numbers. Let's just start with right here. Length of segment FC. I know that F has to be midpoint because G is a centroid, which means BF or segment BF has to be a median, which means that has to be a midpoint. And if those are midpoint, this length and that length is the same. Therefore, the length of segment FC has to be 8. It has to be the same. Now, if I look at something like the length of segment BF, that's this total length. And I know what length of segment BG is. And from B to G is 12. And I'm looking for the full length. I know that the length of segment BG equals 2/3 the length of segment BF. I know the length of segment BG is 12, so let's plug in 12 equals 2/3 length of segment BF. I want to get rid of that fraction because I'm looking for length of segment BF. To get rid of the fraction, you multiply by the reciprocal. So if I have 2/3 there, I multiply this side by 3/2. I multiply this side by 3/2. So length of segment BF equals 3/2 of 12. Well, that's 3/2 times 12 over 1. That's 36 over 2, or 18. So, again, this length from B to G is equal to 2/3 from B to F. I know BG was 12, so I then multiply both sides by the reciprocal, 3/2. 12 became 12 over 1. That's still 12, and I multiplied straight across. 3 times 6 is 36, 2 times 1 is 2. 36 divided by 2 is 18, and that gave me my answer. Now, to do length of segment GF. Well, if I do length of segment GF, that could be considered to be 1/3 the total length. Or I could look at it as 2 times the length of segment GF equals the length of segment BG. I think I'd prefer to do this one. 2 times length of segment GF equals 12. Divide both sides by 2. I get the length of segment GF to be 6. And just as a quick check, 12 plus 6, is that 18? Good. It matches up. It's exactly what I expect it to be. The next one, length of segment AG. Well, right here, I know that the length from A to E is 15. And if I'm looking for length of segment AG, well, that's from vertex to centroid. So length of segment AG equals 2/3 the total length from A to E. So length of segment AG equals 2/3 of 15. Length of segment AG equals 2/3 of 15 over 1. Multiply straight across. AG equals 30 over 3. Or length of segment AG equals 10. And there we go. So at this point, I could do one of these ratios and say like, oh, the length of segment AG equals the length of 2 times the length of segment GE. So let me write that out for you. I could say this at this point. And then find length of segment GE that way. However, I know the length from A to E is 15. I know the length from A to G is 10. So by subtracting 15 minus 10, I get 5. Length of segment GE has to be 5. There's no way around it. If I would have done it one of the other ways, you should have still got 5. Alright, the last two, length of segment GC and length of segment DC. You can go ahead and try on your own. If you've done correctly, you should get 6 and 9 respectively. Alright, the first one I'm going to do, length of segment GC equals 2 times the length of segment GD. From centroid to vertex equals twice from centroid to midpoint. I know that GD is 3, so 2 times 3 length of segment GC equals 6. And last but not least, if I'm looking for the full length from D to C, and I know that from D to G is 3, and I know from G to C is 6, 3 plus 6 is 9. And there we go. We found all those unknown lengths, and we even know the long ones, 9, 15, and 18 respectively. We don't know this segment here, or this segment here, or this one here, or that one there, because there's no way to find it that's necessarily easy. We could, but let's not go there. Alright, the next example says find the coordinates of the centroid given the coordinates of the vertices of the triangle. A is -1, 2, B is 5, 6, and C is 5, -2. So the very first thing that I'm going to do here is I'm going to plot this on a coordinate grid. So now that I have my coordinate grid, I'm going to plot all the points. A is -1, 2, so this is the first point right there. The next one is 5, 6, so 5 over, 6 up, right there. And then the next point is going to be 5, -2. 5, -2, right there. And if I connect all of these here, alright, I'm looking for the coordinates of the centroid. Now, the easiest way to do this is usually to find one of them that is horizontal or one of them that is vertical. But it doesn't matter which point you choose. So, I'm going to just do the midpoint on the right side here. The midpoint will be halfway between on this side. The midpoint formula, if you remember correctly, is x2 plus x1 over 2, comma, y2 plus y1 over 2, and that is the midpoint formula. So if I look, well, it doesn't matter, 5 plus 5 over 2, that's going to be 10 over 2 or 5. So it's going to be on that line no matter what. My midpoint for the right side is going to be 5 comma something. 6 plus negative 2 is 4. 4 divided by 2 is 2. So my point is 5 comma 2. I put the point down over here wrong. It's negative 1 comma 2, not 1 comma negative 2. So here's my midpoint. 5 comma. So in this case, my median is entirely horizontal. Finding the length of this segment is just as simple as counting it up. 1, 2, 3, 4, 5, 6. Or 5 minus negative 1, that's 5 plus 1, or 6. So that is 6 long. Now I know that the centroid is 2/3 the distance from the vertex. So if the full length is 6, well, 2/3 of 6 is times 6 over 1. That's 12 over 3, or 4. So I want to go 4 to the right of the vertex. 1, 2, 3, 4 at this point. The centroid in this case will be at 3, comma 2. The y-coordinate comes from this having all the y-coordinates being 2. This is one benefit to doing either horizontal or vertical median and using the relationship of 2/3, 1/3 to find its location. I could have also said 1/3 of 6 or 2, but then I would have came from the midpoint, 2 to the left of the midpoint. And in this case, 5 minus 2 is 3. I still get 3 comma 2. This method will not work in anything other than a vertical or horizontal median. If you try to do this case and find the centroid, you're going to get a night headache. It is possible, but there's usually a horizontal or a vertical median that they have given you in the book or in the homework. So please do it this way, where you choose the horizontal or vertical median. It'll make your life a lot easier. Sorry, there's a few last things I need to cover, one of them being an altitude. The altitude of a triangle is always the perpendicular segment from a vertex to the opposite side, in quotations, or sorry, in parentheses, or the line that contains the opposite side. So from this vertex to this side, if it's a right angle, this is an altitude. This blue segment is an altitude. But if I look at this case, in this triangle, if I go from here and I try to make a right angle inside the triangle, there's no way I can make from this vertex to a right angle here. So I make a dotted line, and then I make this perpendicular to the dotted line. This is an altitude. An altitude can be outside of a triangle. All the other ones have to at least partially be inside the triangle. The altitude is the one exception. It can actually exist outside the triangle. It's the only one of the 4 that I taught you that can do this. It's the only one that can be entirely outside of the triangle or on its edge. Something to note. Altitudes, medians, perpendicular bisectors, and angle bisectors. These are the 4 shapes I taught you about. In an isosceles triangle, so like for instance this shape down here in the bottom left, this blue segment right here from the vertex angle down to the base, it's actually all 4. This blue segment is the altitude, it's the median, it's the perpendicular bisector, it's the angle bisector. Only in this situation, from the vertex angle to the base, and in an isosceles triangle. So if I would draw a segment from here and made it perpendicular over here, it would not necessarily be an altitude. Sorry, it would not necessarily be a median or a perpendicular bisector or an angle bisector. It's only from the vertex angle here that it's all 4 guaranteed. Another thing, equilateral, equiangular triangle. The altitude, median, perpendicular bisector, and angle bisector are all the same segment from any vertex to the opposite side. So this blue segment here is an altitude. It's also a median. It's also a perpendicular bisector. It's also an angle bisector because this triangle is equilateral. I didn't mark it because it would be a little bit hard to see, but this triangle is equilateral. So this vertical blue segment is all four of the shapes we've talked about. This one here that's also blue is the other example of all four. It's the altitude, median, perpendicular bisector, angle bisector over here. So in an equilateral triangle, they match up perfectly. Every single center will be located right there. All four overlap only in an equilateral triangle. All the centers will be located along this line in an isosceles. Alright, so the last thing I need to the last example we'll be doing is example 4. Is segment AC a median, altitude, or perpendicular bisector? Let's look at this one. Well, it goes from the vertex to this midpoint. It cuts it in half. So this is for sure a median. It is also for sure an altitude. It goes from a vertex and it's at a right angle to the opposite side. And if it's a median and it's an altitude, it is automatically a perpendicular bisector because a median and altitude combine to make a perpendicular bisector. It's a right angle and it goes to the midpoint. This one over to the upper right here, it goes to the midpoint, so it's definitely a median. However, I do not see a right angle, so I cannot say it's an altitude or a perpendicular bisector. So in this case, the only thing I can say is median. So this one was all three. This one was just median. By the way, if 3 out of the 4 match, the last one has to. If 3 out of the 4 match, the last one has to. I don't think there's any exception to that. Yep. In this case, this would have also been an angle bisector. So all 4, just a median. This one here, it's definitely a right angle. It looks like an altitude. I do not know if it's a bisector. I don't know if it's connecting to the midpoint. So therefore, the only thing I can say for sure is an altitude. This one over here, it's isosceles. And it's going from A to C. C being the midpoint. So it's definitely a median. But hold on a second. It's going from the vertex angle to the base of an isosceles triangle. Even though it doesn't look like it, this is also an altitude. It is also a perpendicular bisector. It is also an angle bisector because this is isosceles. This one, if it's one of them, it's all 4. Because it's going from the vertex to the base. And it's an isosceles triangle. So, this one, all 4. This one, all 4. Just median, just altitude. The last thing we need to talk about is the orthocenter. About the neatest thing of this one is really its name. It's the concurrency, or the point of concurrency of the altitudes of a triangle. And this theorem basically says the lines containing the altitudes of a triangle are concurrent. The altitudes will intersect at a point. The neatest thing that happens with the orthocenter is that the point can be outside the triangle. So let's look at the example here. So in this one, this is the orthocenter right here, this point. I can move any of these and it looks like it's staying inside. However, if I make one of them a right angle, whichever angle of my triangle is a right angle, that's where the orthocenter will be located. So if I move this away and made this angle down at the bottom, D, to be a right angle, that's where the orthocenter will be located. So if it's a right angle, the orthocenter will be at a vertex. If it's an acute triangle, it'll be inside somewhere. And last but not least, if I push one of the sides to be obtuse, the orthocenter leaves the middle of the triangle and will intersect outside of it. So the most useful part of the orthocenter will be that it distinguishes between obtuse, acute, and a right triangle. However, you can generally do that just by looking. So yeah, there really isn't a whole lot to talk about with the orthocenter. Yeah, so that's all I really have for you. So you have two new centers of the centroid, which is the point of concurrency of the medians of the triangle, actually has some sort of algebra or some sort of calculation you'll have to do with it. But the orthocenter here, you're just supposed to be able to identify if it's an orthocenter. Remember, it's the intersection of the altitudes of a triangle. The centroid has that length relationship. The perpendicular bisectors is the circumcenter, and that's where I can draw a circle that perfectly circumscribes the triangle. The incenter is the center made up of the angle bisectors, and it's the one that I can construct a circle that will be perfectly inscribed inside of a triangle. Well, that's all I have for you today. Till next time.